Beneath the turbulent waves of the Baltic Sea, humanity is engineering the longest immersed tunnel ever built. The Fehmarnbelt fixed link will stretch across an 18-kilometer marine trench, connecting two nations. Instead of using traditional boring machines, engineers chose a revolutionary immersed tube method. This massive design requires 89 precast concrete segments, each weighing 73,000 tons. The immense geological pressure at 40 meters below sea level demands unprecedented structural strength. We begin our journey at the colossal dry dock casting facility in Rodby Haven, a massive manufacturing hub. Here, a highly specialized grade of self-compacting marine concrete is continuously mixed and monitored. The raw materials are selected with extreme care to resist highly corrosive sulfate ions in seawater. Inside the factory, massive aggregate silos feed the computer-controlled batching plants around the clock. Every cubic meter of concrete is tested for viscosity, temperature, and air content before placement. We are looking at a colossal reinforcement matrix of high-yield steel rebars, densely woven by machines. The steel skeleton must withstand extreme bending moments and seismic forces deep under the seabed. Heavy-duty hydraulic bending machines shape the thick steel rods to a tolerance of just 2 millimeters. Automated gantry cranes lift these massive structural cages into the precision-engineered steel casting molds. A state-of-the-art concrete pumping system delivers a steady flow, preventing any cold joints. Hydraulic thermal sensors are embedded deep inside the thick concrete walls to monitor hydration heat. Excessive internal heat can cause microscopic thermal cracks, which would compromise the waterproof barrier. The curing process is strictly controlled using automated water misting systems inside the casting hall. Once cured, each segment is equipped with massive yellow temporary steel bulkheads at both ends. These heavy bulkheads trap air inside the hollow chambers, allowing the concrete giant to float like a ship. A special hydrostatic test is performed by filling the dry dock with millions of gallons of seawater. The giant concrete monolith rises slowly from the floor, buoyed by the air trapped inside its core. Huge hydraulic winch systems pull the floating structure into the outfitting basin with extreme caution. Here, marine engineers install a complex network of internal ballast pumps and deep-sea navigation sensors. Meanwhile, out in the open sea, the largest dredging fleet in the world is carving the trench. Massive grab dredgers excavate millions of cubic meters of clay and sand from the marine floor. The dredged material is loaded onto hopper barges to be reused for land reclamation in Denmark. An automated sonar system scans the sea floor to ensure the trench depth is highly accurate. The underwater trench must be perfectly level, with a precision tolerance of only 5 centimeters. A specialized gravel bed vessel drops layers of crushed stone down to the trench floor. This stone foundation must support the immense 73,000-ton weight without any shifting. Precision grading tools level the gravel bed, guided by high-frequency acoustic transponders on the seabed. Back in the harbor, 4 powerful tugboats hook up to the floating concrete tunnel segment. The convoy moves slowly into the narrow shipping lanes, constantly monitoring wind and current speeds. A giant specialized immersion barge, consisting of 2 hulls, straddles the floating segment completely. Massive steel wire ropes are secured from the gantry winches to the concrete structure below. The immersion barge carries GPS receivers that sync with onshore base stations for alignment. Underwater acoustic transponders are activated to calculate the exact coordinate positioning of the segment. The maritime authorities establish a strict exclusion zone around the immersion site for safety.
We are here at the new marine development, which is expected to increase shipping capacity by 20%. The project is currently on schedule despite recent weather delays.
The highly critical process of sinking the massive 73,000-ton structure now officially begins. Engineers slowly flood the internal water ballast tanks inside the segment using remote-controlled valves. As weight increases, the concrete giant loses buoyancy and begins its slow descent into the water. Heavy-duty gantry winches on the immersion barge release the steel cables with absolute precision control. The segment descends at a carefully calculated speed of just a few centimeters per minute. Under the sea, deep-sea divers monitor the clearance between the sinking structure and seabed trench. High-definition underwater cameras transmit real-time video feeds of the alignment process to control rooms. Engineers on the command vessel analyze structural tilt, cable tension, and underwater current speeds constantly. Even a minor deviation of 1 degree could cause catastrophic damage to the concrete segment. A sophisticated dynamic positioning system active on the barge adjusts thrusters to counter current forces. The bottom of the concrete segment approaches the meticulously prepared gravel bed on the sea floor. Specialized sonar scanners map the micro gap between the segment floor and the gravel foundation layer. Hydraulic jacks mounted on the temporary steel support legs are adjusted to stabilize the massive load. The weight is slowly transferred from the gantry winches to the seabed foundation without impact. An array of geophones on the seabed records any micro vibrations during the initial touchdown process. Once settled, engineers prepare to execute the crucial mechanical pull to join the tunnel segments. A powerful hydraulic pulling coupler system is aligned between the new and the existing segment. The mechanical arms of the coupler lock onto the internal steel anchoring points of both structures. A force of several thousand kilonewtons is applied to pull the massive concrete structures together. The thick black rubber Gina gasket lining the connection collar begins to compress under pressure. As the Gina gasket compresses, it forms a tight initial seal, trapping water between the bulkheads. Engineers now open the drainage valves inside the chamber to pump out this trapped water volume. The removal of water creates a powerful hydrostatic vacuum between the two massive concrete segments. The immense pressure of the Baltic Sea now acts as an unstoppable natural clamping force. This massive hydrostatic force pushes the new segment firmly against the old one, locking them forever. The Gina gasket is compressed to its optimal thickness, creating a highly durable watertight barrier. A secondary internal rubber seal, known as the W gasket, is installed for double safety protection. With the water completely removed, engineers can safely open the heavy yellow steel bulkheads. For the first time, a continuous hollow corridor is opened deep beneath the marine trench. Now, the temporary water ballast tanks inside the segment are gradually emptied to stabilize weight. To permanently secure the tunnel, a massive sand flow system pumps fine sand under the segment. This pressurized sand fill eliminates any remaining hollow spaces beneath the flat concrete bottom. A protective layer of stone, gravel, and heavy riprap is dropped over the tunnel roof. This heavy stone armor protects the concrete structure from accidental ship anchor strikes and drag. Over time, natural sediment from the Baltic Sea will cover the stone layer, burying the tunnel. The natural marine ecosystem is restored on the seabed, directly above this massive engineering achievement. Inside the dry tunnel, specialized crews begin the long process of pouring the concrete infill. This concrete layer will form the structural foundation for the future road lanes and rail tracks. Every single joint is continuously monitored by high-precision fiber-optic structural strain sensors.
Standing here in the central spine of the new tunnel, the progress is clear. This phase represents a significant milestone for the infrastructure project.
With the structural core of the tunnel fully secured, focus shifts to the massive mechanical outfitting stage. Engineers begin installing colossal high-pressure ventilation fans along the ceiling of the road tubes. These powerful jet fans are designed to control airflow and push out toxic vehicle exhaust emissions. A complex network of heavy steel cable trays is mounted to organize thousands of electrical wires. These cables will distribute high-voltage electricity to power the trains, lighting, and safety systems. Specialized teams begin installing the overhead catenary lines for the high-speed electric train tracks. The electric railway must support train speeds of up to 200 kilometers per hour safely. A robust concrete drainage channel is constructed along the lower edge to collect any water runoff. Heavy-duty industrial sump pumps are installed at regular intervals to clear water from the tunnel floor. An advanced automated fire suppression system with high-pressure water mist nozzles is carefully integrated. In case of fire, these mist nozzles can suppress flames instantly without flooding the vehicle lanes. Emergency escape doors are installed every 250 meters, connecting to a safe gallery. These heavy doors are designed to resist extreme heat, toxic smoke, and pressure waves for hours. A state-of-the-art fiber-optic linear heat detection cable is routed along the ceiling of the tubes. This sensitive cable can pinpoint the exact location of any temperature rise within seconds. We see the installation of high-efficiency LED lighting fixtures, providing optimal visibility for drivers. The lighting system automatically adjusts its intensity based on external daylight levels at the portals. Massive steel traffic signage gantries are bolted to the concrete ceiling to guide future motorists. Electronic variable message signs are connected to the central control system for real-time monitoring. A dedicated digital radio antenna system is installed to maintain uninterrupted emergency communications. All power cables and safety lines are routed to the central control rooms on both coastal portals. Supercomputers now run advanced simulations to stress test the integrated fire, water, and power networks. The automated environmental control systems undergo a series of rigorous power failure testing cycles. A specialized track geometry vehicle runs slowly along the railway lines to measure absolute track precision. Laser scanners on the test train check the overhead catenary clearance down to a sub-millimeter level. Outside, at the massive portal structures, road marking machines lay down clean, reflective guide lanes. Specialized asphalt crews apply a highly durable, stone mastic asphalt layer to the road surfaces. This advanced asphalt compound minimizes tire noise and provides maximum friction in damp conditions. We see the final installation of high-impact steel safety barriers along the vehicle maintenance lanes. Overhead toll gantry systems and speed cameras are powered on and synchronized with central databases. A test convoy of heavy commercial trucks drives through the tunnel to analyze ventilation response. The first high-speed test passenger train accelerates smoothly into the long concrete subterranean tube. The aerodynamic pressure waves generated by the fast train are successfully mitigated by relief shafts. Control room screens confirm all structural sensors are reporting perfectly stable stress levels nationwide. With all checks successfully passed, the massive 18-kilometer subsea corridor is ready to open. This colossal engineering marvel cuts transit times across the Baltic Sea down to mere minutes. The Fehmarn Belt link connects Central Europe and Scandinavia, reshaping global logistics and trade paths. It stands as a solid monument to the sheer power of human mechanical design and perseverance. The boundaries of civil engineering have been pushed once again into the realm of the impossible.
Welcome to the new bypass tunnel. This incredible feat of engineering is set to revolutionize coastal transport, cutting commute times by up to 20%.